Okay, but more recently, so I was, my wife and I, we went to Disney for our 25th wedding anniversary. This is not us, by the way. But we had a great time. And so one of the things that, if you've ever been to Disney, you know, there are crowds.
Yeah.
And so, the thing I want you to think about is as you're walking down the street and you know where you're going, or maybe you're in the high school and you're walking through the hallway and you know where you're going, you have a destination. And so what happens is in an instant, your brain automatically calculates or intuits what's going on. And you see the distribution of the crowd in front of you. And your mind automatically knows the best path for you to get from here to there. And so you take a step. So the shape of the crowd in front of you informs your decision about which way you're going to go. And you know that when there's a small little pocket of middle schoolers sitting right there that make part of the hallway very dense in population, that what you're going to do is you're going to move around them. You don't even think about it, right? You're just like, oh my God, stop talking about that. Go to class. Okay, so we naturally avoid pockets of high density, and when we're in high density, we move slower. Okay, so there's some things here when you start thinking about how do I move through a crowd that are all working together. So we move slower in regions of high density, we move faster in regions of low density, and the shape of the crowd informs your decision about how you're going to move. But now here's the thing. It informs everybody's decision about how they're going to move. And so the crowd all moves together. So the shape of the crowd informs the way the crowd moves all together, which changes its shape, which informs the way the crowd moves. So these two things are working. It's not one happens and then the other. Because you know that as you're walking, you don't wait until you finish the step to look forward again. As you are walking, the shape of the crowd is changing, and you are intuiting continuously. So these things are working together. They're affecting each other. And so I'm working on a project with David Ross here at RIT to try and mathematically characterize how crowds behave. And the original research was done by a guy in Australia named Hughes. And Hughes was worried about incidents of trampling and crushing that happened, right? So we've had some horrible accidents starting in the Hajj. We had a crushing incident in Liverpool. We had this, and so the question is, look, how do we make public spaces safer? So let's try and understand the way that crowds move through spaces. And so this guy Hughes, he was trying to incorporate some of the ideas that we've talked about, okay? And so here are the basic ideas. Now, this is me not talking about the logarithms, but this is like why I would, right, the logarithms come at the end. So what he said was, density changes with position. It depends on where you are. Some places are more dense, some places are less dense. Speed depends on density, right? And this says the derivative is negative, by which we mean the function is decreasing. So larger density, smaller function values. Larger density, smaller speeds, okay? People have a common goal. So in the simplest model of this, we all want to get to the same place, okay? And we all have some common sense of how long it will take. So this is the idea that when you look forward, you look up and you see the crowd, you intuitively know which way you're going to step. Because you know intuitively the fastest way to reach your target, given the shape of the crowd as it is at the moment. So that's this common sense that we all have. How long will it take me to get from here to there? Okay? So this is the multivariable version of the derivative. It's a vector that points in, this vector del phi points in the direction of most rapid increase in, okay, so what is phi? Phi is your sense of time. So this is the vector that points, phi would be the vector that points in the direction that most rapidly increases your time, which is not what you want to do. So you're going to travel in exactly the other direction, the direction that most rapidly decreases your time to target. So this is a characterization of the direction in which you move, but this is, as a vector, the way we calculate it can involve, it can be scaled up and scaled down, it can be big or small, and we don't want actually the size of it, we just want the direction of it. So we divide out the size, and now this becomes just a vector of size 1. When we multiply it by the speed, now we have speed and direction, that's velocity. So this is a characterization of velocity. And it turns out that, so there's a relationship between the speed as a function of density and this gradient vector as a function of position that we don't really need to understand, but it's there, okay? So anyway, here's the problem. So we're trying to take this idea of the crowd, we're trying to say we're all going to the same place, we have a sense of how to get there, how long it's going to take. We know that we move more slowly when things are more dense, right? And so you should think about, as the crowd comes into a space, that it's going to fan out into the space, and where people stop to get ice cream, other people will move around. If there are some slow walkers, we'll cut outside of them and skip around the side, right? So these are the kinds of things that you expect to happen based upon your experience, and we're trying to encode it mathematically so that we can then understand, we can run simulations based on the mathematics and test out different geometries of the space to try and look for spaces, ways of designing public spaces that are safer, right? Rather than taking a horde of a few thousand undergraduates and running them through a space and seeing how many survive. All right, so there's this big complicated equation. What this equation says is that nobody teleports into the space, right? Jim Kirk is not here. Never will be, right? Harry Potter will not apparate into the space, okay? So the thing that I want you to see is that this has, these are partial derivatives, so they're rates of change in particular directions, the x and the y directions. We say how fast are things changing, how much curvature is there, okay? So this is all out of multivariable calculus. And so what we want to do is, so this is in a steady state. So you might imagine, right, so you have a bunch of people walking into one end of a hallway and they're leaving at the other end. And if you take pictures from 1 minute to the next, and fundamentally the crowd doesn't look like it's changing. I mean, different people, right, different clothes, but fundamentally the crowd itself isn't changing. That's what we mean by steady state, okay? So steady state is kind of the easiest way to look at this. It obviously doesn't take care of evolution in time. The fact that the crowd is changing, could become turbulent, that's not captured by this particular equation. It's a time-dependent feature. But this is the simple thing, right? So before you solve a complicated problem, solve a simple problem. So this equation is one that, interestingly, shares mathematical properties with what's called the transonic flow equation, which has to do with the way that air moves over an airfoil. And so when air moves over an airfoil, there's a region in which the equation that describes the pressure, there's a region in which that equation seems to exhibit qualities of diffusion. So like heat diffusion, or you drop a particle of dye into a liquid and there's some kind of diffusive quality to it, right? So this equation, the transonic airflow, has in some regions this diffusive character, but in other regions it behaves like what's called a wave equation, which describes the propagation of information, right? So you've all heard that. That's because the pressure wave moved away from my hand and traveled out to you, okay? And so the equation that describes the propagation of information, in this case the information being the thump, that is called a hyperbolic differential equation. The equation that describes the diffusive quality is called elliptic, and this equation seems to have both of these qualities in different places. So in places where we have low density, we seem to see a kind of diffusive quality. In places where we have high density, we seem to have this kind of wave character. And the thing, and here's the thing, right? So what does that mean? All right, I don't know. That's research. I don't know what it means. I don't know if it's important. I can see that it's there in the mathematics. So one of the things that we might wonder is this. Suppose that we have a crowd, it's moving through a space, and we have in this region of the crowd flow that we have identified as being elliptic, meaning it has this diffusive character. Now, somebody trips, somebody falls. There's a sudden uptick in density because people hesitate, right? Now, we're in the diffusive region. Does that mean that the little uptick in density is going to diffuse over time? Would people just going to kind of go around, we're going to fix, we're going to pick the person up and all, right? Or is in this region where we think the math says diffusion, is that not going to happen? Or maybe let me ask it another way. Suppose that we're in the region where we see that the math says quality of wave propagation. And this very same thing happens, right? So this tends to be in higher density regions. So there's a high density region. Dean and I are walking. She stops short. I bump into her. And now what? So like dominoes, it goes forward and propagates? I don't know. I mean, I just don't know. So before we can start to kind of fight with the math of it, we want to gather evidence. We want to experiment. Just want to try it. But again, right, we can't just run 1,000 undergrads through the quad and see what happens, right? Right, the RAB won't let us do that. So we need to run a computer simulation instead. Okay, so let's run a computer simulation. So in a computer, a derivative, which is a rate of change. Now, let's see, a rate of change, you should be thinking distance per unit time, rise per unit run. It's a difference, it's a change. So in a computer, a derivative is just a difference. So what we do is this. So we set a grid, so here's a hallway. This hallway constricts. And so people are entering on this side and they're exiting on that side, and we have placed on the hallway something we call a curvilinear coordinate system, curvilinear grid. Okay, so at this point here, the y variable is 0.1. At this point here, the y variable is 0.1, because they're on the same horizontal line. So the coordinate system is kind of morphing as you go through the hallway. Okay? And the way it's designed, this coordinate system, is that the y variable is 0 at the bottom and 1 at the top, and it's always that way. So the y variable is the percentage of the distance that you've traveled from bottom to top. Okay? So follow the 0.5 line. Here's 50% of the way, 50% of the way from bottom to top, 50% of the way from bottom to top. Okay? So the coordinate system is not a rectangular grid. And what this does for us, though, is when we do it this way, what I want you to see is if we put like a little node of information at each of these points, what the computer sees is a rectangular grid. The computer says over and up. It has two numbers. It has an x coordinate and a y coordinate. And it thinks that all the x coordinates go from 0 to, I don't know. And the y coordinates all go from 0 to 1. So the computer sees a rectangular grid. That makes our life easier. All right, so we want to compute differences, derivatives. We're trying to solve an equation. And in the case of the diffusion equation, which is related to but not what we're solving, but it's easy to talk about. In the case of the diffusion equation, what happens, you can show, is that the value of the density function at the center is the average of the function values at the neighbors. So you take north, south, east, west, you average them, and if all is well and good, that should be the value at the center. Okay, so it's not obvious, but that's what the diffusion equation says. So, and if you play with it, it becomes obvious, but not when you're first seeing it. So, just politely, please trust me on that. So now here's the thing. So this is how this goes. The fact of the matter is that if we look at the numbers when we initialize our grid, we start up our computer simulation, that this fact that the center dot has the average value of its neighbors that's not actually true. Because we didn't solve the equation, we just initialized something and threw down some numbers and maybe took a best guess. And right, the likelihood of actually hitting the answer with the best guess, right, is probability 0, right? Okay, so what we do then, so here's the method. So this is how we go about solving this, is we look at this spot and we say, what are the values here at north, south, east, and west at the neighbors? Take their average, and once we've computed that, change the value at the center point to be the right value. Just fix it, right? It's like when my son was really young, we told him to take the trash out, and so he takes the trash out to the garage, and he looks at the big trash bin, and he says, I can't get the trash in the trash bin. And I was like, what, too heavy, right? And he says, Daddy, there's a tarp on top of the trash can. Move the tarp, then put the trash in. Okay. All right, so fix the problem, right? So we have a problem. The data's not right. We're not solving the equation. So what do? We fix the problem. So we just changed this number. Sorry. We changed this number. And then we walk up the grid. Whoops. We walk up the grid. We look at the next one. The number in the middle is wrong, so we fix it. The number in the middle is wrong, so we fix it. We keep going. And we just walk over the grid. See, here's the problem. I don't know if you can see it. Think about what I did when I was focusing here. I changed that value, right? I changed that value so that, for the express purpose of making it the average of its neighbor values. And now I just changed its neighbor values. The value at this point is no longer right. So, what do we do? The answer is we finish going over the grid, and then we go over the grid again and we try and fix it. During which time, we wreck it. So we go over the grid again and we try and fix it. During which time, we break it again. Here's the idea. If all is well and good with the universe, maybe even though things aren't right, maybe in this process they're converging toward being right. They're getting better. Okay? And so if that's true, then what's going to happen is that as we go forward and we pass over the grid over and over and over again, remember we have an equation we're trying to solve and the numbers aren't quite lining up. So we're moving over the grid over and over and over again to try and fix it. Each time, because we're approaching the actual target solution, each time the changes that I make get smaller. I have less of a problem each time. So I make an adjustment, and then I'm closer. Not right, but I'm closer. So I make an adjustment. It's still not right, but now I'm even closer. So if all is well and good, and if this system works, what we should see is that the changes we're making from one pass to the next, the changes are getting smaller. Now that's not a guarantee that we're going to converge to a target solution, but there's more going on in the background and we know that we will. So, all right, here is a graph of the change. So what I did was I went over the grid, passed over the grid, and I said, okay, of all the changes that I've made, what was the biggest one? Worst case scenario. And so what you can see here is that as we move forward in time, so these are number of passes over the grid. What's happening is, so this is pass number 500, 600, 700. I passed over the grid 1,000 times. And what you can see is that the worst case change that I've had to make on any of these points, the worst case is dropping. Okay? So hopefully I have suggested to you that this method is converging toward a right answer. Because I'm having to change things by less and less and less each time. Now, here's the thing. So this is, these are, right, 11 times 10 to the minus 4 is the changes that I'm making each time. And then down here, right, 7 times 10 to the minus 4 is the size of the change I'm making, worst case scenario. And what I'd like to say is, like, do you guys, okay, so when am I confident that I'm close? Because you guys know, right, like if I have, suppose that I change my function values by 0.1 for the sake of conversation. I change my function values by 0.1, right? And if I do that, if I change those function values by 0.1, and I do that 10 million times, I could have changed my function by a million, right? 10 million times 0.1, I got a million units of change. Even though each time I'm changing by a very small amount. If I do it enough times, the cumulative effect is pretty big. So, okay, so what I want to know is, so the change is decreasing. The change is small. Does that mean that I'm close to the target? Or does that just mean that I need to do it a million times? Okay, so this is what I'm worried about. When can we say we're close enough to the target, that we're comfortable, that what we're seeing here is right? That's the okay. So, turns out, right, so you might want to say, based upon the computer simulation, 10 to the minus 5, 10 to the minus 6, based upon some other information we know, that's where maybe you want the change to end up. Once you get down there, 10 to the minus 5, 10 to the minus 6, you're confident that this is converged pretty much to where it's going to be. Okay? So, that's what I want to know. How many passes do I need to make over this grid? And really, my question is not, honestly, how many passes. The question is, do I have time to go get a cup of coffee? Right? And, or do I hit run and go home? That's the question. Because I don't want to sit there all day and wait on this thing and be thinking to myself, oh, it's almost done, it's almost done, it's almost, it's. So I want to know, how long is this going to take me to get the simulation to solve the equation for me? That's what I want to know. So, this is the data. This is not from a formula. This is from measuring, right? I make a pass. I said, what was the biggest change? I recorded it. I make a pass. I say, what's the biggest change? I record it. So there's no formula here. I can't just go solve an equation to figure out how long I have to wait. I have data. So here's what I'm going to do. I'm going to say, this thing, I don't know. If I look back at it, I'm like, look, that could be a power law. That could be a power law, like maybe it's 1 over x I'm looking at. X to the minus 2, x to the minus 3, I don't know. It could be an exponential, right? E to the minus x, e to the minus 2x. And those two things, they converge very differently. Exponential stuff, right? Exponential decay converges very fast, super fast, good stuff. Power laws can take a while. So what I want to know is, which one is it? What am I looking at? Because that's going to help me do my prediction. So to find out, I'm going to use the logarithm. This is where the log comes in. Okay? So, what's the log? The log helps us, in science and engineering, helps us to distinguish between power laws and exponential laws. Okay? And here's how it happens. You say to yourself, well, if it were this, what would I see? Okay, so here, if it were exponential, it would look like this. If it were a power law, it would look like that. Now, if I use my logarithm, if I apply my logarithms, so nothing fancy happened here. I just typed an ln in front of everything. Okay. So, but now I'm going to use the property of logarithm, right? So you know that the log of a product is the, I don't know if you know this, do you know this? The log of a product is the, almost, it's the sum, right? Because logarithms are really exponents, so they obey exponent rules. So the log of a product is the sum of the logs, and then here you see that you have a power, right? So it's the log of x to the p. Now wait, if you have a power, do you remember what you can do with it? You can bring it in front, right? Okay. And then here you have log of e to the stuff. And if you have log of e to the stuff, what's that? It's just stuff. Okay. So you have kind of two different scenarios then that you're looking at. In one case, if it's a power law, now, so what, hold on, I want to distinguish here between, so the exponential, it's almost typographic, okay? Just like think, what does it look like? Here, y is down low, x is up high. They're playing different roles. Here, y is down low, x is down low, they're playing the same roles. I mean, in terms of like where they are on the page, okay? So if it's a power law, what I want you to see is that log y and log x are related by a linear equation. The logarithms of the data are related linearly if what I'm seeing is a power law. If I'm seeing an exponential, in which case x and y are kind of playing different roles, in that case, log y is related to x linearly. So if I want to know, is my data linear or is it exponential? What am I seeing? What I'm going to do is I'm going to go and I'm going to calculate the logs of x and y, and I'm going to plot them. And one of two things is true. Either log x and log y are related linearly, or, one of three things is true. Log x and log y are related linearly, or x and log y are related linearly, or, I don't know what the heck's going on. Those are kind of my three options. It's okay? All right. So I think that now we're going to jump. Yeah, here we're going to jump. So okay, so this is a slightly different graph, a slightly different set of data, but that's the kind of thing we were looking at. And so here I have over in my workspace, you see x and y. So what I'm going to do is I'm going to go and say x is log x.
So you've opened up MATLAB.
I'm sorry?
You've opened up.
I had it open before I started, yeah. So this is MATLAB. And y is log y. And so now I can produce a figure, and I'm nothing in the figure right now. So I'm going to plot log x versus log y. Actually, I'm going to plot x versus log y. And I'm going to give this thing a title. So this would be an exponential, because x and y are playing different kinds of rules. So we have to ask ourselves, does that look like a line? I see a bend myself. It looks bowed to me. So, okay. So now let's go and we'll do a next figure, and we will plot x against log y, and we will title this power law. And okay. Better. I think better. So if I had to make a call, I might say this looks more linear to me. It looks like log x and log x are more linearly related. So this looks more to me like it's a power law. It's disappointing. So now, in order to get the power, what I want you to see here so in the power law, the power P is the slope of the line. All right? So what I want to do is come back over here and I want to figure out what's the slope of that line. Oops, sorry. Power law. Okay. So the way that I'm going to do this is really very simple. It's not very sophisticated at all. Do you remember, like, what's the definition of slope? Rise over run. So you need a change in y over a change in x. To compute a change in y, you got to have 2 points. Which 2 points do you want to use? Yeah, how about the first and the last? Right, it's not particularly sophisticated, but it's quick and simple. So I'm a big fan of quick and simple when it works for me. Okay, so here's what I'm gonna do. M is, or this is actually P, our power. So P is y of, now what I can do here in MATLAB is I can just say, go to the end. And there is the first value in y. So this is the difference between y values, last and first, divided by the difference in x values, last and first. So there's our power. There's our power. Now, if we want to check it, so hold on. So no, I don't want to do that. Close that. Figure 3 is the power. So I'm going to do a plot where I say I'm going to plot my x. I'm going to plot these 2 points, first and last. So in MATLAB, what you do is you tell it your x coordinates and then your y coordinates. And there you see. The line's actually pretty close. I mean, it's not bad.
Can you bring that up a little bit, Crow?
It's not bad. It's not great, but it's something to work with anyway. All right, so negative 0.6608. I'd like you to write that down because we're going to need it in a minute. And the other thing we're going to want to know is, so the first value of x that we're dealing with is 500, and the value of y that goes with it is 0.0012. So this is going to be information that we'll use in just a minute. All right. Okay, so based upon our graphs, we think that this is a power law. We think we know what the first point is on the graph. Actually, we know what the first point is on the graph. We think we know what the power is. So, actually, let me back up just a little bit. So what we want to do, what we're going to need to do is this. Right, we're going to need to find out what is that number C. And now we know C and we know P, so we have a power law that will allow us to approximate how big x is going to need to be. That's our number of steps. If we want to achieve a change that is below a certain threshold. Okay? So, now in the abstract, I said there'll be an audience participation component of this. This is it. Right? So 1,000 passes over this grid takes 0.9 minutes. So if I want my change from one step to the next to be less than 5 times 10 to the minus 5, which is a number I just picked, it's halfway through the 10 to the minus 5 range. How long do I need to run the simulation? Right? Should I go get coffee? Should I go out to dinner? Not a rhetorical question. This is not for you guys. I hope you brought calculators.